10.2 Plane curves and parametric equations. All right, most of the time for all of your math career, you have thought of y as a function of x. Well, now we're going to change it up a little bit because sometimes x and y are independent of each other and they both depend on something else. Or y may depend on x, but there may be another element like time or something, and you have a particular orientation where it's not just here's x and here's y, but when x is here, y is moving in that direction or the other direction. You'll see what I mean. So what we're going to do is take a regular y as a function of x, and we're going to introduce a new thing called a parameter. And you see down here I have x as a function of t and y as a function of t. And this works for on some interval. It doesn't have to be from minus infinity to plus infinity, but for at least on some interval, f and f and g are both continuous functions on that interval. And we can rewrite our function or our equation in terms of f being a function of t and y being a function of t. It doesn't always have to be t. It can be anything that you want it to be, but we're introducing this new variable, and the new variable is called a parameter. And when you write it like this, with x equals a function of t and y equals a function, those are called parametric equations. You're still graphing on the xy plane, but now you're plugging in values of t to both equations for x and for y and getting your coordinate pairs that way and examining the behavior of the x and the y at the same time as t does what t is going to do. Once you get this graphed on your xy plane, you have what's called a plane curve. So because x is, your parameter, whatever you choose, in this case t, is moving in a particular direction, then your points on your xy plane curve are going to have a particular orientation, and that is another dimension. I mean, we can think of three-dimensional as x, y, z. You could maybe think of four-dimensional as being the three directions and time, but now we have a different thing to incorporate, and that is the orientation. Which way is it going? Is it going out or is it coming back? Or is it a combination? And you'll see as you start graphing these functions that they will have a particular direction to them. Okay, let's start with an example. Here we have these parametric equations where x is twice t and y is 3 minus t squared. I'm going to set up my plug and chug thing here with different values, t increasing so that I can see the direction that my curve is going. When I'm going to take each of these values of t, plug them into the equation for x and get these coordinates, plug it into the equation for y and get these. And now you see that we have ordered pairs x, y all the way down. We're going to plot these points and connect the dots in a particular orientation. And on the graph, you see that I have the arrows that are pointing in the direction of the orientation. And so as t goes through from minus infinity to plus infinity, and how do I know that? Because these are polynomial terms. There's no domain restrictions. So t is going to go from minus infinity to plus infinity. And as it does that, it's going to come up this way and go through this curve, following along, and it's going to keep going forever and ever in that direction. And you look at the little arrows on the curve, then you can see the orientation. Now, every equation can be written with parametric equations in any way that you choose. And you can use parametric equations of different types to change the orientation or to eliminate part of the graph, or even to make more complicated computations that come later make them more simple, and you'll be using parametric equations in that way when you get to Calc 3. Now notice over here, I took my x equation and solved for t, and then I take what t equals and I plug it into the y, and here I have y as a function of x, and I have eliminated the parameter. Later, you're going to be doing this in the homework. You're going to be eliminating the parameter, or you're going to be taking something like this and writing it as a parametric set of parametric equations. Everybody will probably have different answers. And of course, the most obvious thing is to let x equal t and y equals 3 minus t squared over 4. Let's look at the second example. Here we have x is 1 over t and y is 2 over t minus 3. Now you see right here, t can never be 0. And here t can never be 3. So we have some limitations on our t. So eliminating the parameter here, if I take this equation and I solve for t, I get t equals 1 over x. Now you see x can never be 0. Then I'm going to take this t is 1 over x and replace this t with it like this. Multiply the top and the bottom by the x, and you're going to get y equals 2x over 1 minus 3x. Now notice here that x can never be 1/3. So we have, and that fits with this too, right? If we see from here that t can never be 3, then x can never be 1/3. And you see that also from our final equation. Okay, eliminating the parameter. Don't forget to always check your domain. Look at this next example down here. If x equals t squared and y equals t squared plus 1, and we eliminate that parameter, we get y equals x plus 1, which just looks like this. But because we started with this parametric equation, there's no limit on what t can be. T can be minus infinity to plus infinity. But you see that x equals a positive number because t is squared here, and y equals a positive number plus 1 because you have a positive number. The smallest this can be is 0, and you're adding 1. So we have this domain and this range for this equation that came from the original parametrics. And if you look at just this with no restrictions, you have this line, minus infinity to plus infinity. But if you graph it parametrically, and you start at minus infinity and you go to 0, you see you're starting at positive infinity and coming toward the axis this way. Once you hit the 0 and y equals 1, and you go past that to positive infinity with t, you're going back where you came from. So if you're looking from minus infinity to plus infinity for t, then you're going to get this graph that starts at positive infinity out here in quadrant 1, comes down to the axis, and then instantly turns around and goes back where it came from. Very, very, very useful in the real physical world when we're examining things that behave that way. Now, we need to recognize that theta can also be a parameter. Now, we're going to learn graphing in polar coordinates next, and I do not want you to get confused. If you ever have x and y in your problem, then you are doing a parametric equation, period. So don't let that confuse you. Now we have these two equations, and if we plug in values for theta, and normally we would start at 0 for theta and we'd rotate around, here let me draw it, we would start on the positive x-axis and we would rotate around through theta. We know how to do this, right? So if we start at 0 and we plug in a 0 for those thetas, cosine of 0 is 1, so we'd get a 2. That's this point right here. rotate through quadrant 1 up to pi over 2 and plug that in, and we get cosine is 0. So we see that the x value has gone from 2 to 0 as we rotated through quadrant 1. Now look at the y value. The y value at 0 is 0, but when we get through quadrant 1, the y value is now up here at 1 times the 5, and we get this point. So we've gone from x being 2, y being 0, through quadrant 1, and it just happens to be quadrant 1 on our graph. It will not always be that way. But now the x is 0 and the y is 5. When we rotate through quadrant 2 for those values of theta, then the x value will go negative and the y value will go back to 0. And we're going to get this bit of our graph. And when you're plugging and chugging, you'll get that. But what I wanted to point out is your orientation. You're rotating around this ellipse in this direction. That's where those arrows come from. Now, let's eliminate the parameter. So when you have sines and cosines, you want to use what you know. So we know that sine squared plus cosine squared equals 1. So what we're going to do is take each of these parametric equations and square them. So I'm going to square both sides. This is just multiplication, so there's no foiling going on. If there was addition or subtraction, this would be more complicated. Don't be lazy. If there's addition and subtraction, you have to FOIL. In this case, it's easy. X times itself is x squared. That's a 4 cosine squared, and you get this equation. Now, isolate the cosine squared, you get x squared over 4. Do the same thing for the y. You're going to get y squared equals 25 sine squared. Isolate the sine squared, and you get y squared over 25. Now, if sine squared plus cosine squared equals 1, then we have x squared over 4 plus y squared over 25 equals 1. And this, you should recognize because you did your homework, is the equation of the ellipse. There's nothing being subtracted from the x and y before they get squared, so it's centered at 0, 0. You're going to go out 5 units in the y direction and 2 units in the x direction. And you know I always associate a with x and b with y because it's alphabetical order. So you plot the center, and you're going to go back and forth 2 units, up and down 5, connect the dots, and you see that ellipse. Eliminating your parameter when you are using trig functions is really, really important. You need to really practice that, and you're going to need to remember all of your trig identities to do that. Now, sometimes you're given an equation and it's up to you to find the parameterization of it. So the simplest thing to do is let x equal t. You plug the t right there. There you've got the parametric equation for y. But you don't have to do that. You can pick anything that you want. In this case, I let x be m over 3. Plug the m over 3 in for the x here, and you have your equation for y. You see why I chose m over 3, because when I plug that in, the 3's cancel, and I get simple m plus 2. I can make it as easy or as difficult as I want. I can use the parameterization to limit my domain, and I can use it to change my orientation. I can do lots of stuff with it. So practice that. It's going to come in handy in Calc 3. Now last, I really, really, really want you to look in your book. Example 5 on page 705 is about a cardioid. I'm sorry, a cycloid. We'll be talking about cardioids next. But a cycloid, it's like if you put a ball on a ledge or a circle on a ledge, and you have your pin at a particular point on the circle, and you roll the circle across the edge, and you're looking at the curve that's traced out by the pin. That's what you're getting in exercise 5. When you flip that upside down, you get the upside down cardioid. The Todochrome problem, very interesting. And if you guys are into skateboarding or snowboarding, stuff like that, think half pipe. The half pipe, if it's shaped like a like a cycloid, then no matter where you drop into the half pipe, you're on the fastest path to the bottom because of gravity. The shape of that cycloid is going to cause you to get just enough acceleration at the beginning of your drop in to make it to the bottom as fast as possible. And no matter where you drop in, you're going to get to the bottom in the same amount of time. It's just really cool stuff. And I'm also going to post a video that explains this a lot better than I'm doing right now.